right, so just to remind you, what I would like you to remember are the things, and I have placed it on Canvas, but these are the things that we have seen. So if R, and I use that with capital R everywhere, so even if a lot of times you will see as you move from spherical coordinates where you see R as the radius, the capital R, you go to cylindrical coordinates and you see rho as the radius, all right? It's just because we use different symbols for the different coordinates. I will use capital R here. So if R, capital R, is your distance from the charge, then we know for a point charge, the electric field as you go away from the point charge changes as 1/r squared. You see R cubed, but you see in the numerator I have another R. So the magnitude, the total magnitude in E is 1/r magnitude squared. So you remember that if I have a point charge, as I move away, the electric field that I feel goes as 1/the distance squared. When I go to an infinite line charge, because of this now, it goes as 1/the distance, all right? When I go to an infinite surface charge, this one is constant. Remember that? So every time you go from 3D to 2D and then 1D, you lose 1r in the denominator. So 3D, 1/r squared. 2D, which is the, 2D, well, 3D means the 3D dimension. Let me just go back, I don't want to confuse. Point charge, where I use spherical coordinates, 1/r squared. Line charge, where I use cylindrical coordinates, all right, because it's infinite, 1/r. Infinite plane charge, constant. And here, for example, is what we've seen for a charge which is creating a sphere, all right? Still goes down as 1/r squared, if you see here. Always 1/the distance squared if the charge is three-dimensional, all right? 1/r if the charge is an infinite long line. Constant if the charge is an infinite long plane. Okay, so these are the three things you need to remember. Last time, also, we ended up working on that square. Remember, and what I told you is to use the formulas that we calculated here, and for a finite length line charge, use the formulas, but then consider any shape like the square as made of 4 of these finite line charges. And then you can use the formulas to find the electric field wherever you want. However, what we also said is don't exactly run into formulas immediately, but try to think physically what happens. And what we've learned by doing this last time is that the center of this square charge, the field is 0, because all of the charges around exert forces or electric fields that eventually cancel each other, all right? And they cancel each other because it's a perfect square. Thinking of that, if I move from a perfect square to a circle, and I show here all of the derivations, all right? I take an infinitesimally short piece of the circle, and I write the field in terms of that, and then I integrate around the circle. And what I find is this expression here for the electric field everywhere, as a matter of fact. However, on the line, everywhere along the line that goes through the center of the circle. I'm not looking at other places, and I will explain why, but through the line that goes through the center of the circle. Okay, what do I see there? I see that when z equals 0, which means I am right on the surface of this circle, is 0. The same thing that happened with the square. All right, because why? Because all of the charges around the circle will cancel each other. So, however, as I move north of that, then z is not 0, and then I see that I have a component which is along the z direction. All right, and that component is dependent on z, and you have the formula here. The one interesting thing also is the following. If you assume that rho is much smaller, assume here, and that's what I want to show you. So when you have the formulas, you watch the formulas, you try to understand of what they're telling you physically, all right? So if I have this, and that's what I want to help you understand here. If I have this charge, all right, what this formula tells me is that if z, so I'm looking at here at the center of the charge, and I'm looking along the z direction, right? So if I am very close to the circle, my field gets very weak. So it starts at 0 at this point, at 0. And then as z increases, that increases. However, so for example, if I were to plot the field, the E sub z component of the field here, and that's your E sub z, then it starts at 0. At some point, it starts increase. Well, it's not, as soon as you move away from z equals 0, it starts increasing. And then as z starts getting bigger and bigger than r, all right, so let me write here so you can explain then to me. So as z, if z becomes much bigger than r, what happens? E sub z is qz over 4 pi epsilon naught, and then r in front of z is much smaller, so I can write z squared to the 3 over 2, which is z cubed, which is then equal to q over 4 pi epsilon naught z squared. So what does that tell me? It tells me that if I move away from the circle, it starts growing up a point, and then it starts going down as 1 over z squared, all right? And when does this happen? When I move so far away from the circle that all of the charge, it seems like it's 1 point charge. So if the circle is this, and you're down there trying to find the or you move away. So let's assume that I have a circle here. This is the circle, and I say all of this circle that I have exactly this size here is a charge. If I'm next to it right where I am, I see, in fact, if I get here, I will see all of this perimetry around me. If I am where I am, I see still this in a relatively big size. But if you're down there and you start, probably you see that as almost a dot. So what that tells you is that while I'm close to this, I start seeing the geometry, but when I'm far away, I see like 1 point, 1 charge. And therefore the field, the far field as we call it, because this is a near it, this is a near field, but the far field down there is gonna vary as the far field of a point charge. which is 1 over r squared. 1 over, in our case, is z, the distance, all right? 1 over z squared. 1 over the distance squared. That's what, rather in terms of r or z. 1 over distance squared. And that's why a lot of antennas, now this is an antenna, you see, very badly made. Dipole. I see it, I'm here next to it, because I'm very close to the antenna. I will see geometry, the field that I feel, if I were to measure it right here, it will vary along the side of the antenna. It will vary around here and all of this. But if you go down there and you try to measure how this antenna works, you're going to see it points out. So your field from a distance out is going to vary as 1 over the distance squared. So that's why those things are important to you. This is physics. This is how it tells you how the fields vary. And you need to have that capacity after you take this class, not to remember the equations. The equations is like you read a poem. It's like you read a story. You don't remember the words at the end after you read the book. You remember the story in the book. Is that right? Well, that's what I want you to know. When you leave this class, I don't want you to remember what the book said, what Professor Katehi said, what I drew on the board. I want you to remember the story about the fields, how they vary, what they do, the impacts they have, and so forth. The story is that matters, all right? Okay, so pay attention to that, because next week I may give you a problem that involves some things like this. All of the derivations are here, but don't solve problems without understanding what you're looking for, because a lot of times you will give me solutions that make no physical sense, and you will not be able to understand that it makes no physical sense because you think, oh, I got it from this equation. Don't trust the computer or the equations. They will give you whatever junk you put in. As I say a lot of times to my graduate students, we put junk in, we get junk out, all right? Equations don't mean anything unless you use them carefully, and you only use them not to tell you the physics, but to tell you details that your major story may not be able to give you unless you go down into the weeds, for example, okay? So this is what we have covered so far. Today, we are gonna go into the next chapter meaning in the next group of concepts, and we'll start with the potential and the voltage that you have used. I'm sure you have seen it in your circuit classes, but we're gonna talk about potential and voltage in terms of an electric field. Because always you need to remember, even if you go to circuits and they tell you whatever they tell you in circuits, they don't tell you the real story. The story behind it is left for this class. There is no voltage in any circuit that is not the result of an electric field. Okay, there is no such a thing as voltage. That is not the result of an electric field. That is not the result of a charge or a current that flows. All right, so, but you took it, you say, well, it is the potential difference, okay? You define somehow the potential at the time, maybe without using much of an electric field. But in reality, in true physics, is the force, the electric force. We are in statics, all right? The electric force, the electric field, and then the potential, which gives rise to voltage, that which eventually we use in circuits, which are macroscopic representations of electromagnetic problems. Everything is an electromagnetic problem in electronics, everything. Now we skipped that chapter because we thought it was not worth knowing. But in reality, we made a huge mistake by doing that in our education. Because the bottom line is everything is a result of the field. And yes, if you use a circuit that is DC or very low, all right, and you're not in very high frequencies, all of this is fine. I mean, you can put circuits down, you know what you're doing. However, that is not going to stay too long the way it is. Let me just tell you that as we go to 6G, you have heard about 6G? You know what is 5G? Okay, we'll talk about that some other time. But in 6G, which is the future of wireless communications, the future of everything, of every edge device we are going to use. In 6G, we are going to start using terahertz frequencies. What is a terahertz frequency? You remember, like kilohertz, all right? What do we have kilohertz for? Audio, go down, all right? Megahertz, what do we use megahertz for? TV, all right? FM, radio. Gigahertz, what do we use gigahertz for? Our communication here. 2.5 or 5 gigahertz. Sometimes 21, it's all here. Now we are using. What is 6G? 6G is the next generation, where we have to go to very high frequencies to be able to accommodate a lot of bits per second. What is terahertz frequencies? 800 gigahertz, 800, 10 to the 9 gigahertz. Well, the circuits now we are learning are not like those circuits anymore. If you try to design the circuits for those terahertz radios, if there are, they say they're going to do for what? You know why we're going to use terahertz? The people say 6G to have holographic communications. Why do we need for a holographic communication to have gigahertz? Because the bits per second will be terabits per second to have a holographic communication that people aspire to. How do you move terabits per second if you don't have enough frequency band, which we cannot get a low frequency? You go up to 840 gigahertz, and then even a tiny slice of the band gives you a lot of frequencies. So the circuit design that we guys all learned, I did, you are, is not going to apply the way we are teaching it anymore at those frequencies. So what I'm saying, in your profession, which is going to last, hopefully like mine, for the next 40-some years, you're going to see substantial change, and those things will be extremely important. Physics will never go away. Models will go away, but the foundational physical interpretations will always be the same. Okay, so that's as a bit of a motivational kind of a discussion. Next, what we are going to do, by accident, I put it here, and that one has to go here and here. Okay. All right, let me think. And that now I'm going to write also here, other page. Okay, let's write first. How do we define work? Do you remember how you defined work? Okay, let's see. How do you define work when you move a load, a 5 kilogram kind of it? When you go to the gym, for example, and you pump weights. Well, how do you know how much work you spend when you do that? How will you figure out how much work you spend when you raise a 100-pound bar? Yes. Force? Go ahead. Yes, you said force and distance, and what else? Okay, let's assume it's good enough. I mean, there's going to be mass involved in there too. But in some ways, yeah, the force you apply on the mass you raise divided times the distance. All right, that's the understanding of the work you put. You are, of course, you don't do it like that way, because automatically you look at the calories. So you look at the energy. You're going to know how many calories you spend. That's why, but it's work involved, and energy is the work over time. All right, you need to remember. So the same thing applies when we have a charge and we try to move a charge. The charge is here. All right. Let's assume that we have an initial charge that creates an electromagnetic field. This one an electrostatic rather, creates an electrostatic field like this. All right, all around it. And this little charge that is here is feeling a force. And if this is Q1, Q2, this one, and this is Q1, the force that you see is Q1 times Q2 over 4 pi epsilon naught. And if this is the distance between the two, you call this R, then is A sub R. Let me write it this way so it has that direction. A sub R divided by R magnitude square. All right, that's what we learn. Okay, now if I want to take this charge Q2 and move it, let's assume I want to take this charge and move it from here. In fact, I used a different color from this one. I want to move this charge from here somewhere else. This position Q2 prime. I will have to exert to do work to do this. All right, I would have to do work to be able to do that. And if this distance were to be infinitesimally small, all right, so let's assume that I don't want to do this much of this. I don't want to go this far away, I should rather say, but I want to go just a bit away. Let me erase this. So for example, let's say in the beginning, I want to go, instead of out here, let's see how much it's going to cost me to go here and assume that this force, because this is a small distance, let's assume that this distance is going to be a dl, all right? I then have to move this over this distance. Then I will have to apply work, which I will call it dw, all right, because it's a short distance. And then if I divide this, which dw is going to be nothing else but f dz, all right, for this simple case. And then if I divide this by Q2, this is going to give me what? It's going to give me what I call a change in potential. All right. So work is going to be over a small, if I want to move a charge over a small distance, that small amount of work that I will put dw is going to be f dz, the force times a dz. And why did I start with infinitesimally small? Because then I don't have to consider that far away, the force is going to change. I assume if it's only a small displacement, then the distance of the charge from that charge Q2 of the charge Q1 that has created the original field is going to be about the same. All right, that's why I can simplify my equations. And so if I have a charge within an electric field, electrostatic, then it feels a force. If I want to move this charge by a bit, then spend a little bit of work, then it's practically the force times the distance I move it. If I divide that by the charge, it gives me a new concept, the concept of the change of potential. All right, what does that really mean? It means, what does potential mean? Do you know what a potential means? The potential is really a measure of the type of energy that you have in that given location. For example, when I am very high up on a mountain, all right, on top of Kilimanjaro, for example, and then I go down, then when I'm in the top, I have the highest potential in terms of, mechanical potential, if you like, if you call it like that, because of the gravity. All right, so to go up there from the base, I have to spend a lot of energy. So as soon as I spend energy, by being there, I concentrate energy in the following way, that if somehow I was up there and then all of a sudden the mountain behind me disappears, I will fall down without having to spend any energy. All right, I mean, you see a ball, you have to push the ball up to raise it. But when you leave it from the floor up, all right, you spend work. You spend exactly work. So, however, the moment you have it out there and then you let it down, the work that has already been, the potential that has already been accumulated here, it allows it to fall down without any extra energy. So that's what the potential really is a measure of the different energies you have in your system. If you spend energy to go someplace, that means that if you were to come back, you will not spend any more energy. All right, so for example, if the charge, in our case, if the charge Q1 is here, Q1, and Q2 was here, and then I moved Q2 like this to this position, so I spent energy to move Q2 in the Q2 position. All right, I spent energy. If I then let Q2 prime flow free, it's gonna come here to this position without spending any additional energy. So that what that tells me is that I have increased the potential of the charge Q2 prime in the new position. And so if the potential here was V1 and the new potential here, or V2, call it, and V2 prime, if the potential in the initial position of Q2 was V2, and then now I have increased it because I put my extra work to move it to the new position, and that's V2 prime, all right? Then if I were to let this charge Q2 prime flow free, it would come to its initial position. So I have a differential. I have a differential energy, level of energy available. And that is called voltage in circuits. All right. So what do you say when you have a circuit? When do you say I have a resistor and I have a voltage of like 2 volts across the resistor? The resistor is 50 ohms. What does that mean? That if I let it free, that is going to create a current, all right, automatically. Because I have already accumulated energy on one side from the other, and therefore is going to allow this flow to happen. And so without any force, if you have a particle or a mass at particular high energy, without any force to sustain it there, it's gonna try to go back to where it was initially. So in any system, the system will try to go into equilibrium. Equilibrium means to equalize everything. Equilibrium in a circuit is when you have zero current. When do you have zero current? When the voltage everywhere is the same. Do you agree? That's equilibrium. But when you have differences of energies, then you force charges to move around. And for circuits, that's a good thing. Now we pay for it, we have a battery. This operates because we force charges to move around. Where do we get the energy for that? From the battery, all right? So we pay for this if we want charges to move around. If we have zero battery, what happens to this? Goes to equilibrium. What does equilibrium mean for your phone? Dead. That's what it means, all right? When you don't have enough power and you cannot talk to your friends, you cannot see anything, equilibrium. There is no voltage difference anywhere. Nothing moves, all right? That's a system. That's where the systems automatically go. So the potential gives you the difference between the electrostatic energies. And the voltage is that difference, all right, that we use the name. And we've, of course, all of these theory in words, we write it mathematically. And mathematically, we have introduced the concept of the potential using the electric field, which is the right way to use it, because we are talking about electric energy, all right? So potential is a scalar, all right? When I say I have more, when I say that the student has more potential than another, what does it mean? That the person has put a lot more work and knows more things. We use it also potential in the real life. We use it the same meaning. So in electrostatic cosmos, if you like, in electrostatic world, potential shows the various levels of electric energy, all right? And therefore, of the electric field. And there is a very simple formula that we have introduced to explain the potential, which is this one. And it says that the gradient of the potential, remember gradient? We saw that for temperature, now it's for electric potential. The gradient, negative that, is the electric field. So what does that mean? Let's try to think of this here, because there is a negative sign, and that negative sign is very important. All right. When you have when you have two charges, Q1, or one charge, as a matter of fact, Q1. And let me see how I'm going to say that. Forget about, okay, you have two charges at this moment, and then I will remove the charges after I introduce them. Q2, all right? So Q1 and Q2, they have established an electric field among themselves. And let's assume now that this electric field applies, and I call this position A and this position B, and I remove the charges for a second, all right? But I do have these two positions, and I have an electric field. I just have removed the charges from the picture, and I have an electric field that is being created between these two charges. And for a second, let's assume that the one charge that I had here was positive, the other charge that I had here was negative, and then, and we think of that, the electric field has this, all right, as we have seen. So that means that the electric, if there is that kind of distance between the charges, that means that the energy at this point, or the electric field at this point, the charges are different, will be higher than the electric field at that point. All right, I mean, if you consider as vector. So you have E1 and E2. And also you will assume that this one has a potential V1, and this has a potential V2. All right. Now, what do they say in the expression? That this E field is the negative differential of the potential, which means that if V1 is larger than V2, the E field is going to be equal to V2 minus V1. All right, let me see this V2 minus V1, negative of this, of course. Let me erase that to make it, move it further out. Okay. If therefore there is a potential, a change of potential between the two positions because of the electric field V1 and V2, then the E field is the negative differential of V, which is practically the negative of V2 minus V1, which is V1 minus V2, which said already the energy at A was higher than the energy at B. And therefore, the potential goes from of the electric field, the direction is from the higher potential to the lower potential. That's what it says. All right. So when you have a resistor, and then you have a battery here, which direction will the current flow? All right. So practically, the reason we do that is the current flows this direction because of a, what would I say? So the voltage between these two, so this is say V1 and this is V2, V1 minus V2, that's what you write. It's gonna be IR, okay? So in this particular case, the field also goes along that direction. All right, so the other thing, let's think of a capacitor. I mean, we are gonna see that in the capacitor, I don't wanna include it right now. But in any case, so we define this relationship with a negative to show that as there is a difference of the potential, all right, the electric field will go always from the higher potential to the lower. That's gonna be the direction of the electric field. All right, that's exactly what it means. And that's how we define it. So the potential is important because it just shows the level of energy, all right, that you have to, or work you have to spend to move one charge from one position to another. And because that's expressed in terms of the electric field, then it explains also that the energy from the initial to the, there is work spent to go to the other position, all right? And therefore, when you define the potential in there, the negative sign creates us a consistent set of relationships that we see it macroscopically as well. And then that really gives us what we have in, it's a definition. The negative sign was extremely important for us to be able to develop all the theory about circuits and everything else. All right. Any questions about that? So the potential, it's a level of energy that is involved in different places. All right. And the difference between two potentials gives you the voltage that applies in a circuit. It's more of a circuit concept. If we were to stay with fields, we would keep only the potential in place. Okay, so here, for example, that's what it shows. It shows you have a given now electric field established, and then you try to move a charge. This is a little more complex because I was moving only one charge, but from one place to a little smaller distance away. This one shows you that this applies even when you move a charge between 2 points, P1 and P2. All right. And according to this, they change, all right, between the, in fact, the electric field here. Well, it says, it shows in fact how if the, so we spoke about when the distances were like kind of very small, and then we had a differential in there, but now you can extend that to distances further away where it's going to involve an integral. All right, and why is that? Because you remember when I wrote here this relationship, when you have small distances, you assume that F did not change, but when you have large distances, then the F from the force from one point of your electrostatic space to another point changes. And therefore, to be able to find the total work, if you like, you will have to integrate, all right? That's why when you go into this definition, you see integrals involved. And that in fact gives you an expression for the electric field in terms of the voltage. V2 minus V1 is called the voltage between the 2 points. And that's what we are using. Okay, so what is the relationship between potential and electric field? What kind of a relationship is it? It's a differential relationship. It involves a derivative, okay? So the electric field practically is a derivative of the voltage. You need to remember that. So at this point, having that said, I would like you to open the TabHat for a moment. So open TabHat. Let me see. I'm gonna get it. There, okay. Again. All right, we go to TabHat for us. Okay, here. Here. Okay, you go to exercises. You go to 4th week. I'm going to here, and I make this. I assign it. And it says the following, and I want you to do it now before you go. On the basis of what I said, you should do it easily. It says the electrostatic potential in a region is a function of the rectangular coordinate x. And Vx is shown here. Consider the electric field intensities at point A, B, C, D, and E, and find where the largest field intensity, at what point is it going to be. At what point between A, B, C, and D, and E, if that were the potential, your electric field is going to have the largest value. And then you will have to say here, oops. Okay, and then you want to say down there of where it is largest. So do this now, and you should be able to finish it before the class is over. And now with that, so finish it, and then I will tell you when it goes before we